Okay, so we've talked about the geometry of the second derivative with concavity and all of that. So now let's go on to some real-world examples. So let's look at example 3 from the text. Example 3. Example 3 from the text. Okay. It says the value of the consumer price index from September 2013 through August 2014 can be given by this figure here that they show. They give us a picture, and they give us a function, and they give us a domain for the function, where t is time in months, where t equals 0 represents September 2013. For some reason, the bounds of their domain does not include that 0 point. That's okay. When the CPI is increasing, the U.S. economy is experiencing inflation. That means that the derivative is positive. Okay, so blah, 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 blah. What else? Inflation rate is given by I prime of t over I of t. Okay, what do they want? Use the model to estimate the inflation rate in January 2014. Was inflation slowing or speeding up in January 2014? When was inflation slowing? When was it speeding up? When was it the slowest? I think they mean to say when was it the fastest there. I think that's what they meant to say. Because, well, anyways, okay. So, consumer price index from is given by this function I of t is equal to negative 0.0225 t cubed plus 0.390 t squared minus 1.20 t plus 234 with the bounds 1 to 11. T equals 0 represents September 2013. And we measure inflation rate. So inflation rate is given by inflation rate. We could just, they actually say this in the problem, could just measure it by just the first derivative of I, but this is a relative inflation rate. That's why we're dividing by the original function, just to get a relative rate. And it is given by a percent. So part A says to estimate the inflation rate in January 2014. We want inflation rate when t equals 4. That's January 2014. If September 2013 is 0, then that would be October, November, December, January. So t equals 4. So we need I prime of t. That's going to be power rule on this thing here. We're going to get negative 0.0675 t squared plus 0.780 t minus 1.20. And now we're going to say the inflation rate when t equals 4 is going to be I prime of 4 over I of 4. So let's see, I prime of 4, so plugging in 4 here and here, calculator tells me that is 0.84. Plugging in 4 into the original function, here, here, and here, I get 234. Huh, that's weird. Is that right? Yep, okay. And that's going to be equal to 0.36% per month. So it is a percent. So you would get 0.0036 and then write it as a percent. Okay. So there we go. There's the inflation rate when t is equal to 4, in other words, in January 2014, according to this model. Was inflation slowing or speeding up? So it's definitely positive. It's going up. It's going up. It's a positive percent, right? The inflation is going up. But is it going up quickly, or is it speeding up? Like, should we expect in the next month that it would be higher than this, or is it slowing down? Will it be lower than this? It's a question for the second derivative. Question of what is the sign of the second derivative? This corresponds to asking what is the sign of the second derivative. So let's get the second derivative. There it is. Negative 0.135 times t plus 0.780. So is it positive or negative? Well, that depends on what time frame they're asking for, right? What t value. And they ask, is it slowing or speeding up in this same January 2014, which is t equals 4. So I double prime at 4 ends up being positive. So inflation is speeding up. Positive concavity or positive second derivative means concave up. It's curved up. So inflation is speeding up. Let's look at the graph and see if that makes sense. Can I put it here? Are we going to be able to see it? Oh, actually it's the same on both pages. Okay. So nope, can't really kind of see it. We're looking at the 4 spot, January 2014, which is right here at t equals 4, and we see that it is concave up there. It's positive. It's speeding up. It's speeding up. Okay. Part C says, when is it slowing, when is it speeding up? When was inflation? When was inflation? The inflation rate slowing down or speeding up? Well, that's asking where is the second derivative positive? Speeding up. Where is the second derivative negative? Slowing down. So we'll take that second derivative, which was I double prime of t is equal to negative 0.135 t plus 0.780. Set it equal to 0. We're going to find the point of inflection by setting the second derivative equal to 0 and solving for t. T should be positive because t is time, and it will be positive. I'm getting approximately 5.8 months. Approximately 5.8 months. So, is it slowing down on the left or right of this? Well, we actually have the picture, so we don't need to start checking around. We could try t equals 5 in the second derivative, and, well, actually, we know that it's positive on the left, right, because we already checked a number that's lower than 5.8, so it's positive on the left. And we could try, like, t equals 6, plug that in, and see if we get a negative value. But we already have the picture, so let's just use the picture that they provided, and it's roughly, how far does it dip? Okay. Roughly like that. Clearly, let's see, this is roughly the 5.8 mark, so 1, 2, 3, 4, 5, 6, etc. So here's 6. So the point of inflection is roughly there, and clearly it's concave up here, concave down here. So, and there's the point of inflection. So, inflation rate, what does that mean? Inflation rate was speeding up. Now it's basically always going up, right? Isn't the slope, except for here and here, the slope is almost always positive of this graph. Where'd my pen go? It's 0 here, but then it's like positive, 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 positive slope, all the way up until right about here where it zeroes out again. So for most of this time, inflation is going up. But remember, this is asking when is it speeding up and slowing down. Not just when is it going up, but when is it going up fast? When is it going up slow? So inflation rate was speeding up where it's concave here, where it's concave, and that's from 0 to 5.8, and slowing down, slowing down on 5.8 to, what was it, 11. Yeah, they're bound, right? Now, they asked where it's slowest, but they mean to ask where is it fastest, surely. I think that's what they mean. Let me see what they said, because they say where is it, or when is it, they say when is it the slowest, but I really think they mean when is it the fastest, because that would be the point of inflection. Yeah, they even answer when is it the fastest in the problem, so I think they mean to say when is it the fastest. When is this inflation rate growing at the fastest? Well, remember, that's going to be the steepest slope, right? That's going to be the point where this, okay, where this is growing at the fastest rate, and that's going to be at the point of inflection, which is t equals 5.8 months. We didn't actually find the y value of this for this function, but they didn't ask for it, so it's okay. Let me say something here before I end this video. I think I may have said, when is it growing the fastest here? That's not what I meant to say. Growing the fastest would be a question of when is the second derivative the highest, which we don't have that information explicitly written anywhere here. What I want to ask is, when is it the fastest overall? Just when is it the fastest? Not when is it growing the fastest, but just a more basic question of when is it the fastest? And that's going to be at that 0 point for the second derivative, when its acceleration has speeding up, and then that point right where it starts to slow down again, that's when it's going the fastest. Right before it starts to slow down again, that's when it's the fastest. Right there, at roughly 6 months. Okay, so let's, I forgot to give some homework problems from the geometry section. So let's say homework for that will be 17 through 23 odd. And I think there was one more for the what was that? Did I give that one? Tell you what, I'll just do them all at the end. I'll just write it all down at the last video. How about that? Okay, so example 4 from the text is another real-world example concerning the point of diminishing returns. I actually recommend that you actually read example 4 because it says it has 3 really good pictures of each graph, the original graph, the derivative, and its second derivative. What we're going to do is we're going to take this function they give us, which is 1 over 1 plus 50 times e to the negative 0.2 t, and this is million units sold. So this is some sales function. Output is in number of units sold. T is measuring time, where t is in months. Okay. I'm going to split this example into parts. I'm going to say part A, find the rate of sales the rate of sales. So this is sales, and I want the rate of sales, which is going to be the first derivative. And also find the acceleration of sales. Which is the second derivative of the sales function. First of all, s prime of t, that's going to be a couple chain rule applications. So the inner function is 1 plus 50 times e to the negative 0.2t, and the outer function is 1 over t. So we're going to take the derivative of the outer function with respect to the inner, so that's going to be negative 1 over t squared, except it's not t, it's with respect to this function, so that entire denominator squared, and then times the derivative of the inner function. The derivative of this, the 1 will go away, we'll drop that negative 0.2 times 50, what is that? Negative 1 e to the negative 0.2 t. That's no. That's not what that is. Oh my god, I don't know. It's 10. Had a brain fart there. Negative 10 e to the negative 0.2 t. And we can clean this up and say negative times negative is positive 10 e to the negative 0.2 t over this denominator squared. Okay, there's the rate of sales. How about the acceleration of sales? Second derivative. So this is going to be interesting. Alright, it's going to be a quotient rule because we've got to take the derivative of this function. It's a quotient of two functions of t. So it's going to be, there we go, derivative of the first, well, derivative of the numerator. So I'm just going to set it up first. Derivative of the numerator times that denominator minus, dang it, I'm gonna need to go to 2 lines for this. Really don't want to though. Let's retry. Let's write it smaller. Okay. Second derivative of s with respect to t. Okay. Derivative of the first, so 10e to the negative 0.2 t prime, that's going to be the derivative of the numerator, times the denominator, minus the numerator, times the derivative of the denominator, oops, 1 plus 50e to the negative 0.2, all squared, all over this denominator squared, which will be 1 plus 50 e to the negative 0.2 t, all to the 4th power, because remember, if you square something that's already squared, you raise it to the 4th power. Okay, so I've got all my derivatives set up. Go ahead and copy down that denominator. Alright, derivative of this function here, derivative of this function, or this part, will be negative, what did I do here? Dang it, negative 0.2. Negative 2e to the negative 0.2 t times this, so I'll just copy that, 1 plus 50e to the negative 0.2 t all squared, minus, so this just gets copied down, now minus this gets copied down, so 10e to the negative 0.2 t times the derivative of this, which is going to be a chain rule application. It's going to be derivative of the outer with respect to the inner. That means I'm going to drop this exponent, copy down that inner function, times the derivative of the inner function, the derivative of this inner function, writing with a Sharpie sucks. Okay. So times the derivative of this inner function will be 50 times, so another little mini chain rule happening here. This drops down, makes this negative 10 e to the negative 0.2 t. So this goes there, and then we will say close that. This parenthesis matching with this parenthesis. And we can just leave it like that. It's pretty ugly. If we could clean it up a bit, but this is fine. Okay. They didn't even do this in the example because it gets so nasty. Alright, part B. So we found the rate of sales and the acceleration of sales, which looks awful. Okay. What do I want to say here? Part B isn't really a question. I suppose it's more, well, interpret. So they give us these three graphs, and I actually want to say interpret the point of inflection and what it means geometrically for each of these graphs. They give us s, so the actual function that they gave us, s, the original s function, its graph looks like this, and this steepest slope, well, actually, let me draw all three, and then I'll start talking about what they mean. Alright, somewhere in the middle, this is s prime. So this is s prime, and finally the second derivative, which looks like that. Okay. Now, they tell us that the point of inflection is happening somewhere around 20.
Babe, I gotta do an interview.
Okay. Okay, so where was I? Let's see. So we're interpreting what the point of inflection means in each of these graphs. So each of these points is definitely interesting for each of these graphs. So the point of inflection in S is the steepest slope, right? That's where the slope is the steepest. Let's call it, it's a point of inflection in this graph, but we wouldn't call it a point of inflection here and here. We're going to call it something different. So let's say the t equal to 20 point in S is the steepest slope. The t equal to 20 point in S prime is the flat spot, is where slope is 0. That same point in S prime is where S prime has an x-intercept. That's just three different interpretations of the same point in three different graphs. So in the original S graph, that point is a point of inflection where the slope is the steepest. It's where acceleration is 0. What does that look like for the graph of the S prime, which you can think of as a speed or a rate? That's going to be where the slope of that rate is 0, where the rate is a maximum, right? That's maximum speed. It reaches maximum speed, then it turns around and slows down and starts going back down. And for S prime, that corresponds to a 0 for the actual graph, which makes sense because that's how we find these points of inflection. We take the second derivative and set it equal to 0. So it's an x-intercept. It's an x-intercept where S prime goes from being positive to being negative. That's where a point of inflection happens, where the second derivative goes from being positive to being negative.